Hello everyone. In this video, we are going to talk about input circuit in VLSI chips. Input circuit is an important and integral part of VLSI chip design. It basically has two functions. One is protecting the digital logic from the external voltage trace and noise. Voltage trace basically caused because of the electrostatic discharge, because of both human, machine as well as packaging. In the previous video, we have discussed about the electrostatic discharge and this protection network used to protect the internal logic from this electrostatic discharge. Apart from this, another important responsibility of input circuit is to decide the compatibility of the IC with the other technology. So input circuit is the one which decides the compatibility of the given IC with the ICs of other technology. In digital circuits, many ICs have to communicate with each other, so they have to be interfaced along with each other. Now, for different ICs, the voltage level VIL, VIH, VOL, VOH may vary based on the technology used for the fabrication. For example, suppose we have designed a MOSFET IC, then its VOL, VOH will be very high. So when uh, it is connected, another IC of TTL series connected in cascade with that, then VIL of TTL IC should match with the VOL of this MOSFET IC. VOH of this IC, MOSFET IC, should match with the VIH of TTL IC. So input circuit is the one which decides the compatibility of different IC. Uh, so it shifts the input voltage of a particular IC to the compatible voltage level. So we'll discuss this in detail in next few slides. So one of the circuit, which is the simple circuit, which can be used for the input circuit, is input series transmission circuit. As name suggests, it basically consists of a transmission gate, uh, which can be seen here. Okay, so if you look at the block diagram, basically there is a transmission gate and there is an input, and this input is coming from input pin, and the output X goes to the logic, digital logic. So here you will be having various MOSFETs implementing the logic for your IC. Now, uh, there is a signal called as enable signal which acts as a strobe, which allows the signal to pass from the input pin to the digital logic when or it blocks the signal from passing from the input pin to the internal logic. So basically it will act as a tri-state. Uh, if you look at the implementation, MOS implementation of the same circuit, you can see here there is an A input pin and there is a protection network. There is of course the pin will have some resistance which will be represented with the lumped component over here. So there is a protection network. We have seen two types of protection network in earlier video. One which uses diode and another which uses the uh, high oxide thick oxide MOSFETs along with the diode. Here there is a transmission gate. At the input of the transmission gate, there is a input signal, or the output of protection network goes to the input of the transmission gate, and the output of the transmission gate is connected to the digital logic. So where actually the logic is built is the input is applied to the logic gates. Uh, Now the controlling input or the strobe is controlled basically by an cascaded inverter over here. You can see there are two cascaded inverters and they basically controls the enable signal. Now let's look at the operation of the circuit. Okay, when E is equal to 1, okay, E is equal to 1, the output of first inverter, this is first inverter, output becomes 0. So 0 is applied over here. So 0 goes to the input or the gate of the NMOS. And then same 0 is applied to the input of the next inverter or cascaded inverter. Output of that inverter become 1, which goes to the gate input of PMOS. and as the gate input of NMOS is 0, it is off, and gate input of PMOS is 1, it is also off. So input, even if there is an input at A, let's say there is a logic 0, but still it won't go to the logic implementation in an IC, right? So if the enable signal is 1, that means it acts as a tri-state or a buffer. Actually, there is high impedance state. The input won't move past, input won't be applied to the output, or rather input won't be applied to the logic of an IC. Now in case when E is equal to 0, so when E is equal to 0, input of the first inverter is 0, so output is 1, that is logic 1, of course. So the logic 1 voltage is applied to the gate input of NMOS. Logic 0 will appear at the output of the second inverter, and at the gate inverter of the PMOS, logic 0 volt will appear. Logic 0 will be applied. So because at the input of gate input of NMOS is logic 1, so it is 1, so it is on, and at the gate input of PMOS there is a logic 0, so it is also on. So whatever appears at the input pin after passing through protection network, it goes to the internal logic of an IC. So this is a simple input series transmission circuit. That circuit can be used for the as a transmission circuit. Now there is one drawback or limitation of this circuit. Here you can see whatever voltage appear at the input. So suppose there is a TTL circuit connected over here, and let's say it's VOH. Let's say its VOH is 4 volt, right? So if it is not compared, and there is a MOSFET circuit with for which VIH is, let's say, 4.2 volt, let's assume this. In that case, the voltage won't be so TTL is actually generating logic 1 output, but because it is less than VIH input of the MOSFET circuit, it will assume it to be logic 0, right? Because there is no shifting of the level of an input in this kind of circuit, right? So that's the limitation of input series transmission circuit, because it's just simply either blocks the input or it allows the input to move to the logic of the MOSFET, MOSFET logic of your IC, right? So that that limitation can be overcome in another simple circuit, which is nothing but an inverted input circuit. So it is a simple inverter used after the protection network. So here you can see in the block diagram, you can see there's an input and there's an inverter circuit basically, which acts as an input circuit, and then there's an output circuit. Of course, just with the apparently you can say that one of the limitation of this type of circuit is the input is inverted in an inverted form. So when your circuit is expecting to have A, you will actually get A bar. So the input is inverted form. So of course it can be managed by connecting another inverter, or you can design your logic accordingly with the inverted inputs. That can be done, but that's the first impression when it comes to the mind, that if you are using an inverter, you have the input which is going to be at the input of your logic, MOSFET logic, will be inverted one, right? So if you look at the MOSFET implementation, a very simple circuit, just an inverter you have to connect. But if you look at the working of this, we are trying to basically work on the limitation of the earlier circuit, that the transmission gate input circuit. Suppose you have connected a TTL circuit, okay? Let's say it's trying to apply logic 0, and its logic 0 voltage is nothing but let's say 0.8 volt, right? And here there is a MOSFET logic, so you have implemented some logic using MOSFET, NMOS and PMOS, CMOS. Let's say you have used CMOS. Now for this, its VIL value, let's say it is 0.1 6, right? So in this case, it apparently there is no compatibility between this input and or logic 0, which is for the TTL, won't act as a logic 0 for MOSFET, because the voltage can be 0.8, which is greater than VIL, so it can treat it as logic 1. But in this case, the input circuit plays an important role, right? So here you can see basically there is a simple circuit with the PMOS and NMOS. Okay, so we basically have to design, we have to basically work on VIL and VIH of this circuit. And as it is a CMOS circuit, its VOH will be VDD and its VOL is basically 0 volt, which is very much compatible with the internal MOSFET circuit logic, right? So what we have to work on is VIL and VIH of this circuit. So we have to make sure that the VIL of this circuit, if there is a TTL, should be less than, it should be less than VOL of this TTL circuit. Let's assume there is a TTL circuit, and VIH, sorry, uh, VIH of this inverter should be greater than VOH of this circuit, right? So that's the basically idea, and you can do it. This can be done by adjusting the W by L ratio of these PMOS and NMOS. So once you design it accordingly, the MOSFET operation, inverter operation, you know. So if there is logic 0, obviously this PMOS will be on, because you have to just make sure that this logic 0 is read correctly from the TTL logic, and you have to design this W by L ratios properly. So once it is logic 0, then it interpreted logic 0, so it will be on, and logic 1 will appear here, so which is nothing but a VDD, which is very much compatible with this internal logic of your IC. Okay, and suppose there is a 1, then this will be on and it will be pulled down to the ground, so there will be 0 volt, which is again compatible with the voltage level of your internal logic. So that's a very simple kind of circuit, and it can be easily shown that this inverter input circuit work well with the TTL series or TTL ICs, so that used for the compatibility. A simple circuit, if I can draw, would look like this. If there's a TTL and there is a, let's say, CMOS circuit, a simple design would look like this. Suppose this is the VOH and this is let's say VOL and VOH of this TTL circuit. Then we have to just make sure that uh, that yes, so we have to make sure that VIH of this CMOS inverter, basically we are talking about the input circuit, so basically we are talking about the CMOS inverter, should be, if this is the value, it should be greater than sorry, it should be less than VOH of the TTL, and if VOL has this value here, then you have to make sure that the CMOS should have VIL greater than VOL of this circuit. So basically the noise margin that you have to manage, of course there is something called a threshold voltage VT that you have to design. So if you want to so I'm not going to discuss this in detail. If you want to if you are interested in the details of this, then you can refer Kang. So it is explained, some calculation is given in that book, you can refer to the book. Yes, so that's the circuit. And then the next simple circuit is non-inverting TTL level shifting input circuits. So one of the, not disadvantage, but you can say limitation is that here the output X was inverted version of input A, right? So your logic has to be designed accordingly. Now this can be overcome by basically connecting another uh, cross-coupled MOSFET connection or MOSFET circuit before the inverter circuit. So let's look at the working of this circuit. Okay, so let's say the input is applied over here. Now here you can see that it acts as a TTL. In the block diagram it is shown as a buffer and not as an inverter. So basically there is no inversion of an input. Okay, so if the input is applied to the pin A, then it goes to the protection network and it basically clamps the input voltage. So it makes sure that it won't go beyond a certain level to the lower level, or that is negative level, and the positive level of the voltages, and then it is applied here. So let's say it's logic 0, or say 0 volt. So in that case the 0 is there, so this will be off, right? So the same voltage 0 will appear here. Okay, so here you can see the gate of this is connected to VDD, so it is always on. So here it is on, so the 0 voltage is applied here. As the 0 voltage is applied there, it is on. So logic 1, I mean this is on. So as this is on, so basically this line will be pulled high, or this point will be pulled high, because this is on. So there will be logic 1, so this is off, which is very much uh, according to our assumptions. And then the VDD is applied at the input of this inverter, so which is 1 volt, and then at the output you will have 0 volt. So basically the logic which you have implemented using MOSFET will get 0 as an input. So we are expecting input to be 0, and the output we got 0 as an input. So it basically has overcome the disadvantage of the simple inverter, that the input is in its real form and not in the complemented form. Okay, let's check this for the logic 1 as well. So if the logic 1 output is there, so it will go to the protection network. Let's say logic 1 is, let's consider for the TTL, logic 1 is, let's say 2.4 volt. Okay, so if the 2.4 volt is applied here, so that is logic 1, so this is on, right? This is always on, so this is on, because this is on, so this is pulled to the ground, right? And that means here the 0 is applied. So at the input of this MOSFET 0 is there, so it is on. So this point is at VDD. As this point is at VDD, so this is off. So here you will have 0 volt. Okay, so at the input of this inverter there is a 0 volt, so it will invert this 0 volt to give you logic 1, and which will be compatible with the TTL, or sorry, CMOS logic that you have implemented, that is 5 volt. So 2.4 volt that you had at the input of this has been converted to 5 volt. Typically the threshold of this will be very small, like 1 volt or something. So the 2.4 volt, even if it is 2.4 volt, it will be treated properly as a logic 1. Same is in the case of logic 0. So when we discuss about the logic 0, we didn't consider actual voltage, but this can be easily proved that it will be treated as logic 0. So that's a simple circuit which basically acts as an input circuit, and it can be used as a compatibility circuit, or basically the circuit which level shift the TTL compatible input to the MOSFET compatible input. Yeah. So the next type of circuit is the input pad with the Smith trigger. Now in this case you can see here it is used as an op-amp. So if you look at this symbol, it is basically an inverter with the Smith trigger. That means it will be always pulled to the VDD or minus VDD, or to the highest voltage or to the lowest voltage, right? Yeah. So here you can see basically if you look at the circuit, uh, there is one inverter, and inverter is extended with by using another PMOS and NMOS, and from the common point of this another NMOS and PMOS uh, are taken out, and from this common gate of these the output is taken out. Okay, so if it's logic 1, input is logic 1. Okay, so after going to the protection network, sorry, so after going to the protection network, you can say logic 1 will appear here. So because logic 1 will appear here, this will be off, this will be off, and this will be on, and this will be on. So these are on, as both of these are on. So voltage at this point will be 0, voltage at this point will be 0, So because this is 0, so this is on, right? So as the 0 appears here, so we will have 0 volt here, right? So input was 1, again it got inverted to have 0 over here, right? Now, next is, let's say logic 0 is applied here. So if logic 0 is applied, this will be on, this will be on, this is off, right? So voltage at this will be logic 1, voltage of this, that is VDD, and voltage at this will be VDD. Okay, so because of this, this will be on. As this is on, so voltage at this will be VDD, this point. Okay, but this will be pulled down. So this is VDD. No, it won't be pulled down. So VDD will appear at this input, and here that is logic 1. It will be treated as logic 1. So basically, it is inverted. Okay. The only point we have to consider here, when it is VDD, actually it won't be VDD, but it will be VDD minus 2 times the threshold of this voltage, these PMOSes, right? Uh, that we must consider. So it acts as a Smith trigger because it always pulls input to the upper highest voltage, that is VDD, or to the lower voltage, that is ground. So basically, it acting as a Smith trigger. So this is another type of input pad. So there are, of course, with the advent of the technology, there are more input circuits which are used here. So uh, that's about the input circuit. So we have seen the basic type, and you can see you can find different variations or variants of this input circuit. Normally, they are also termed as input pad. So if I just consider the circuit, it's called as input circuit. But then along with the protection network and this pin, it is called as input pad. Okay, so that's a common term, input pad, output pad in the other side. Okay, thank you. We'll stop here.